good afternoon. Welcome back. It's a great honor to be here. Thank you very much for the invitation. And I'm very excited to share with you some of the deepest images we have taken of our cosmos today. I don't know, do I have to press that the slides are coming or? Okay, so yeah, as George was saying, we'll talk about the star formation in some of the very first galaxies. And so we are diving into some of the deepest images we have taken so far. But of course, when we want to understand how the images such as these came about, we have to really start basically with the Big Bang. And so here I show you an image of the universe that probes basically the structure 380,000 years after Big Bang, as imprinted on the cosmic microwave background. And it's these small, tiny fluctuations that basically grow, and in particular, dark matter fluctuations grow to form so-called dark matter halos that lead to the large-scale cosmic web. And when we then think about, and the success of this standard cosmological model is that we can not only understand these fluctuations in the cosmic microwave background very far back in time, but we can also self-consistently then predict the large-scale structure that we observe today in the universe. Now, when we think about galaxies, we can look at, here the cosmic web. Galaxies are actually forming in the very centers of dark matter halos, and you can see that they are basically very tiny in comparison with the large-scale cosmic web, right? We are zooming in here, a scale by about the factor of 1,000,000. Now, as you will see in my talk, that for the processes to understand galaxies is actually also important to not just understand the large-scale structure, but also the small internal workings of galaxies that are related to the sites where star formation takes place and the evolution of black holes. And so I put here a few, kind of key physical ingredients that are important for the evolution of galaxies, starting out with small-scale processes related to stellar winds and supernova feedback. But then, we have large-scale processes, just gas flow in and out of galaxies. And the challenge to understand galaxies is really, that as you can see here, that galaxies are spanning a wide range of different spatial scales, but also different time scales. And we cannot really observe how a galaxy evolves by studying an individual galaxy, because we can observe the galaxy today, tomorrow, and the day after tomorrow, and they still look the same. But we really need to kind of understand how the physics of galaxies works by studying galaxy population across cosmic time. And so the very fundamental paradigm for galaxy evolution is that we start out with these small perturbations. The dark matter fluctuations basically grow, and then we have the baryons, in particular the gas, that falls into these dark matter potential wells and is able to cool. And when you think about the formation of the very first galaxies, we of course have to think about the formation of the very first stars, population 3 stars that basically only consist of hydrogen and helium. Now, JWST has actually a hard time to detect those stars directly, and 21-centimeter experiments or gravitational waves will be, probes that are probably more successful in directly tracing the first stars. Then when we go to more massive systems, you can see there that basically we have atomic cooling taking place. And so we have the formation of the very first galaxies, roughly about 100 million years after Big Bang. Until then, we have more mature galaxies forming later on. Now, the last ingredient to understand actually for the growth of, understanding the growth of galaxies is feedback, which basically means that the stars that you are forming, but also the black holes, they somehow have to prevent overcooling. And you can see this very nicely when you look at the number density of objects. I show you here the number density of galaxies as a function of their stellar mass. And you can see that when you compare this with the dark matter halo mass function, that you need to regulate the galaxy growth both at low masses and at high masses. And this is exactly where basically the current frontier lies, try to understand what kind of physical processes are there that basically leads to this preventive growth of galaxies, both in the low mass end, but at the high mass end, when we look at dark matter halos. So putting this into basically cosmic time, you can see very much on the right is the Big Bang. We have recombination where we transition from an ionized to a neutral universe. We had this phase of dark ages before then the very first stars and galaxies started to form, starting cosmic dawn. Again, this is roughly 100, 200 million years after the Big Bang. And then we entered the epoch of reionization, where basically the universe was turned from being neutral to being ionized again. And then we had the key epoch of cosmic noon. And this is really, where you see basically that most of the stars in the universe have formed. You can see that the cosmic star formation rate density, the quantity that basically tells you how many stars you form per cosmic volume, you can see that that peaked around a redshift of 1 to 3, which corresponds to a look-back time of about 8 to 11 billion years. And so, yes, so if you want to understand, for example, how the star formation in the universe played out, we can build up very simple models. We call them regulator models or bathtub models, where you basically say that a galaxy is this very simple system where you have gas inflow, you have the formation of stars, and some of these stars then produce feedback and basically blow out the gas again. And so in such a model, you basically say, well, the star formation rate in a galaxy should just be proportional to the amount of fuel you provide. And so if you're doing this, you can write up this very simple equation where you say, well, the star formation rate of a given dark matter halo at a given redshift, at a given epoch, should be just the star formation efficiency times the baryon accretion rate. And then you have to calibrate this model, and you can do this empirically via matching, for example, a stellar mass function or a UV luminosity function. And you can see you get this star formation efficiency that basically peaks around the halo mass of 10 to the 11. Again, this shows you that you have to somehow have less efficient star formation, both at low masses and at high masses. And in this very, very simple model, there is no physics associated to that. You get this naturally out by basically empirical constraints. But of course, you can run more complicated models and say that, well, the low mass end is dominated by stellar feedback and the high mass end might be dominated by black hole feedback. Now, if you take such a simple model, you are very naturally able to actually reproduce the overall evolution of the cosmic star formation rate density, right? You can see that basically we expect that the amount of star formation in the early universe is rapidly rising by orders of magnitude over just a few hundred millions of years. And the reason for this strong increase is basically just this convolution of understanding how do these dark matter halos build up with cosmic time. And I show you here the star formation efficiency, and overplotting now the halo mass function. You can see that the abundance of dark matter halos that are able to host efficient star formation is drastically increasing at these early times. And so this leads to basically this drastic increase in the cosmic star formation rate density. And you can see these were pre-JWST constraints. And so this model was, basically well accepted, a very simple model to explain this early increase in the cosmic star formation rate density. There are, of course, other models, right? You can, for example, tune the star formation efficiency with redshift, and you would get, higher star formation rate densities in the early universe. Now, of course, this is exactly where JWST comes into play. We want to constrain the early star formation because that's where basically most of the physics when it comes about stellar feedback lies. And so with Hubble, we had really good rest frame optical capabilities, all up to about redshift of 3. Again, this is probing 10 billion years of cosmic time, so there's really a lot to learn already. But when we go to higher redshifts, where the data points get sparser, we are only probing the rest frame UV, which of course limits the amount of constraints we can get from these observations. And with JWST, this is of course drastically changing. We are now able to get basically large-scale surveys done, with probing the near-infrared emission lines up to around redshift 2, and then really probing the rest frame optical out to about redshift of 8 or 9, which really means that we can probe basically the rest frame optical out to the epoch of ionization, and then again probing the highest redshift universe, cosmic dawn epoch, with the rest frame UV. And this allows us now to really answer some of the most fundamental questions when you think about galaxy formation evolution. Again, there will be, of course, much more discussion on galaxy evolution, I think, on Thursday, but it's related to understanding how the galaxies build up their structure internally, bulge and disk formation, how do galaxies chemically enrich, and also how does actually star formation regulation works. Now, today I will focus more on kind of the highest redshift regime, in particular focusing on how do the very first black holes and galaxies start to shine in the cosmic dawn epoch. Now, there are a wide range of different surveys, and I don't have time to basically go through all of them. I myself am part of the JADES team, which is a GTO program that is, basically GTO time from NIRCam and NIRSpec. But you can see here a wide range of different surveys that basically, show you a wide range of different pointing strategies, as well as depths and filter sets. And of course, this helps us to shed light on the large-scale structure with kind of shallower surveys, but getting basically large areas, and then some very deep drillings where it helps us to constrain the faint end part of the luminosity function. Now, the JADES team is a large collaboration, and Marcia Ricci and George Ricci are both, playing leadership roles in this collaboration together with Roberto Malino as well. So a large fraction of the team is actually also here present. And one of the main goals was really trying to probe the earliest galaxies in the universe. And so I show you here this image, which probes basically 1, 2, and 4 micron. it shows around 40,000 galaxies. So there's a lot of galaxies to explore. And you can look at these images also online and scroll around and click actually on these objects to learn more about them. I just want to zoom in on one of the subregions here to basically highlight the diversity of galaxies we have in those images, right? You can see here kind of nearby galaxies, maybe a redshift 1 or 2, that are kind of in white in color, and then you have these dust-obscured systems that appear redder, and then the small speckles that are kind of really far distant galaxies. Here I'll show you a comparison to what we had with Hubble Space Telescope previously. So on the left, it basically shows you the deepest image we had, the Hubble Ultra Deep Field in the H-band, which is 1.6 micron. And on the right, we have the same patch of the sky, but now in the JADE survey. And what you can see are two things. One is that we have a much smoother background, and we are able to pick up, sources that were hidden in the background before. And then you can see that when we look at the foreground galaxies, that we are able to actually see star-forming regions spatially resolved in much better detail. Now, the important part, I think, is that as part of this, as part of the JADE's team, is that we try to really combine and build synergy between imaging and spectroscopy. So we used imaging to find the most interesting objects that we wanted to then characterize physically in greater detail. And I'll show you here one example. You can see on the top a prism spectrum, which basically covers, the full spectral range that we have in NIRSpec. And then on the bottom, you can see a zoom in where we also have a higher, a higher resolution spectrum that allows us to, for example, pick up broader components in these galaxies, which are indicative of outflows. Now, what did we learn from these surveys? There's actually a lot of, has been going on in the first few weeks and then over the last 1.5 years overall. And there has been basically this remarkable result that the bright end of the UV luminosity function is remarkably constant. So when you look at this figure on the upper right, you can basically see that the constraints that we are currently getting out from the James Webb Space Telescope is that the star formation rate density was higher than what you would have expected from Hubble, but also from the simple constant star formation efficiency models. And again, there has been a lot of, let's say, diversities in results. And I think there are a few challenges that we are currently trying to work out. At the beginning, there were questions about calibrations and noise properties in general about photometry. But then even when you think about selection techniques, different teams used the same data, but different selection techniques, which led to a different lists of high redshift galaxy candidates. And so therefore, it's actually very important that we go and follow up those galaxy candidates because they have only been photometrically selected. And this is actually very tedious work, as you will see in a few slides. One primary example of this is, for example, this galaxy candidate at redshift 16. Again, this would be roughly 200 million years after Big Bang, or a look back time of over 13.6 billion years. And what you can see there is basically that there are a few data points in yellow, and the spectrum that is fitted to it basically shows this strong break, which puts it at the photometric redshift of 16.4. But in the literature, it was very quickly being picked up that it might be actually a low redshift interval offer because you can get the same spectral feature, the same photometry basically, with a spectrum that is consistent with being a dusty starburst galaxy. And interestingly, there were neighboring galaxies that were at a similar lower redshift solution of about redshift 5. And then again, thanks to JWST, we are now not able to just find those objects, but now also characterize them with spectroscopy. And so this shows you basically that this galaxy indeed has strong emission lines and puts it at the redshift of 4.9. And so again, I want to highlight here basically that this spectroscopic characterization is fundamentally important. And as part of JADES, we were the first team that really successfully was able to find some of the highest redshift galaxies. In particular, we have currently the redshift, record holder. Here are 4 galaxies. 2 of them, the bottom ones, have been known before being high redshift candidates based on the Hubble images in the Hubble Ultra Deep Field. But 2 of them have then been newly discovered with the NIRCam images, and then followed up a few days actually later with NIRSpec, which was kind of a busy few weeks or days actually to follow them up. And we successfully confirmed the redshift to be above 13, 12, 11, and 10. And thanks to these redshift measurements, we are then able to characterize the physical properties of these galaxies in much greater detail. In particular, we have measured stellar masses of the order of about 10 to the 8, 10 to the 9 solar masses. So this corresponds to roughly 1 billion solar masses. And the star formation rates in those galaxies is actually very comparable to something like in the Milky Way galaxy. So about 1 to 2 solar masses per year of new star formation. And you might say, well, this seems to be quite low, right? Are these galaxies even growing? But if you are computing the specific star formation rate, or basically the mass doubling timescale, those galaxies are actually double their stellar mass every few tens of millions of years. So they are actually rapidly growing. Another thing that you might see is that in the images, these galaxies are very, very compact. You measure sizes of a few tens or up to about 100 parsecs, which imply very high star formation rate surface density. So these galaxies seem to be forming stars in a very, very compact configuration. Now, this is per se not very surprising. We have expected at least that some of these galaxies should be detected at these high redshifts. Again, these are, when you look at the magnitude limits, they are basically kind of intermediate bright. They are not the brightest objects that we know about. The very brightest object in the early universe, when we think about redshift 10 and above, is actually GNC 11. And this galaxy has been around actually for quite a while. It has been discovered with NICMOS, that was mentioned also by Marcia this morning. So Richard Bounds at that time was mentioning that, oh yeah, it's detected in the H band. We cannot really rule out the possibility that it corresponds to a redshift 9 galaxy, but we consider it very unlikely. And this is because it's so very bright. You can see on the bottom right, absolute magnitude versus redshift. GNC 11 lies at the upper right corner, which means it's very, very bright given its redshift. So what's going on? So we have been getting a lot of data actually a year ago on this object. So the first thing is basically, again, the imaging data, which shows that this galaxy is rather compact. It seems to have actually several neighbors around it, which might imply that this galaxy is not alone, as it might be part of a larger overdensity. But the most astonishing result that came out is basically the spectrum. You can see this on the left. Again, here, this galaxy is so much brighter that we can get, in a few hours, a very nice high signal to noise spectrum. And you can see many different emission line features tracing, more enriched elements such as, carbon and nitrogen. And now, when we think about the morphology, we have actually been developing a lot of new codes that allow us to measure the sizes of these very compact images. So the idea is that we are actually forward model all individual exposures, which helps us, to overcome basically just an average stack of the image in the mosaic. So we can get many different pixel realizations around the source. And what we are able to basically do is take apart the galaxy into a core, like a point source, and an extended component. Now, from the photometry alone, we actually can describe this system to be, highly star forming, basically going through a nuclear starburst in the bulge formation-like process. But when we look at the spectrum in more detail, we find that this galaxy also hosts actually an accreting black hole. And this is mostly because of the P Cygni features we see in the C4 line, but also when you look at the high densities that are implied from the permitted lines. And so it's interesting because this basically means when we go and measure from the magnesium line, from magnesium doublet and the N4 line, the black hole mass, we infer that this galaxy has a black hole of the order of about 1 million solar mass already. And when you put this into context, right, you basically see that this is actually kind of a stepping stone trying to understand how these very first black holes in the universe form, how, what's basically the seed mass distribution, and how this relates to more massive black holes that we observe at later cosmic times. An interesting result is that when we look at the black hole stellar mass relation, is that these galaxies and also other galaxies at slightly lower redshift, they lie above this relationship, which means that it seems that these galaxies have assembled supermassive black holes very early on. And so in summary, over the last year or so, there have been several different programs looking into this. And what we find is basically a wide range of different black hole masses, but most of them lie above the black hole stellar mass relation. And they seem to show a rather wide range of accretion rates. So it seems not that all black holes are actually just rapidly growing. Some of them are also kind of in this downturn phase, as you can see here. So why are there too many galaxies above redshift 10? Well, again, I think we need to be conservative. We have to first confirm their distances, and I showed you some examples of how we are doing this at the moment. We also have to assess the contribution from accreting black holes from HENs, but there are also other physical processes we can think about. So for example, one thing is to actually change the star formation efficiency and move away from this constant star formation efficiency model. And so there have been this idea that when you are in a very low metallicity environment, you might have a delay on stellar feedback, which then induces a very high star formation efficiency for a few million years. And this could lead to an increase in the star formation efficiency, at least above redshift 10. There's also the idea that you might change the dark matter power spectrum or the dark matter model in general. So in principle, you can play around with cosmology. There, I think one has to be quite careful because, of course, it has a wide range of different baryonic physical processes to play with. So there's a strong degeneracy between changing, again, star formation efficiency, for example, with the underlying cosmology. There's also the idea that one can just generally increase the scatter of how one goes from halos to UV luminosities, for example, with star formation variability. We can, for example, have more stochastic star formation early on, which would also lead to an increase in bright galaxies. And finally, there has been quite some discussion about changing the initial mass function. We expect this to happen at some point, but observationally tracing this, I think, is very challenging. We find very intriguing objects. For example, Cameron Dahl showed this object where it seems to be dominated by pure emission lines and nebular continuum. But you can also get very good fits to this object, for example, with an AGN-like model. So there is, I think, quite interesting debate going on how we can actually trace a change in the initial mass function towards earlier times. So how can we go beyond redshift 12? Because a lot of the things we are currently doing is really focusing on redshift 9 to 12. And the reason for this is that in the first cycle, the cycle 1 and cycle 2, we mostly focused on broadband photometry with a few medium bands. And this is really to this degeneracy, as I kind of highlighted with this redshift 16 galaxy, that we can basically fit a Lyman break, a high redshift galaxy spectrum, as well as a dusty emission line dominated system. And the way to actually differentiate between these two different scenarios when we look at photometry only is to go to actually medium band. And so we have been putting together this public large program in cycle 2 called the JADES Origins Field, which builds on top of the JADES program and really focuses on medium bands. And here we are talking of exposing basically the same pointing for about 40 hours in certain medium bands to really get a very strong constraint on the Lyman alpha drop. And so again, this should lead us, this basically delivers, nanochansky photometry, in 14 NIRCam bands. Basically, this means 30, AB magnitude depth in those filters. And this hopefully leads us to some of the robust detections, out to redshift 15. And so we have been putting together this list of candidates. Again, this is a single NIRCam pointing, and you can see here our 11 high redshift galaxy candidates that lie between redshift 11.5 to 15. And again, they seem to be all rather compact and rather highly star forming as well. And currently, so you can use these then to basically forward model the selection function and constrain the UV luminosity function. And again, what we find is basically consistent with what previous literature values give you, that we have a rather constant bright end, but overall the UV luminosity density decreases by about a factor of 2.5 from redshift 12 to 14. And again, the spectroscopic confirmation of those systems are currently ongoing. And so I just want to give you a very brief overview of where this stands, trying to incorporate basically everything we have currently in the literature. So we have roughly 400 high redshift galaxy candidates, from all the major extragalactic surveys. There are more than 20 spectroscopic confirmed galaxies. The points that you can see here are currently the ones that are published in the literature. And we are currently working on additional high redshift galaxy confirmations. Again, there is one very bright one from the GLASS team that is currently in preparation that is about redshift 12. And again, it's similar in brightness to GNC 11 that you can see as kind of a green triangle on the top. And the currently record holder that we have not published yet, is basically probing redshift 14, between redshift 14 and 15, which means that we are looking at galaxies now that are about 280 million years after the Big Bang. Again, you imagine that this light has to travel for about 13.6 billion years towards us. So this is pretty amazing and very exciting. So in conclusion, so again, I think it's fruitful, but actually also necessary for understanding the high redshift universe to combine imaging with spectroscopy. We have JWST, showing us that we have overabundance of UV bright galaxies at the redshifts of 9 to 12. We are still we are still working on spectroscopically confirming those galaxies. There are a wide range of different physical processes that can explain this overabundance. For example, bursty star formation or an increase in star formation efficiency. We were able to spectroscopically confirm the first galaxies above redshift 13. So this is, I think, a big success for JWST. And again, GNC11 shows us that actually we can also probe black holes out to, the cosmic dawn epoch, which I think is very exciting. And so in summary, I think this just shows us that the central regions of galaxies, so they are very actively forming in their cores, both stellar mass, but also black holes very early on. And so I think, the takeaway here, I think, is that JWST works beautifully. So thank you very much.